So it would be, how many quizzes have we had since the last exam? Is it 1 or 2? So I guess it'll be, have we had 3? Let's settle this one first.
They should be 30.
So we had an exam on June 28th. So this was lecture 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is today. So 8, 9, 10 will be on next week's exam.
Okay, no, I was thinking about the quiz.
So quiz 1, 2, 3, 4, 5. Quiz 6 and 7. So with last week's quiz, and then the one you're taking today.
6, 7, 8, 9. No, I'm not talking about the in-class quizzes. The campus.
So that would be 8, 9, 10.
Oh, that's the homework.
Yeah. The homework is numbered the same as the lectures.
8, 9.
Today's lecture is on solutions. In lab, a number of times, you have been told to use a bottle of 0.1 m sodium chloride, something like that. How many knew what the 0.1 m meant?
Isn't that how much it's said?
Right, it's a measure of concentration. So some of you may have known it was a measure of concentration, but it looks like maybe no one knew exactly what it meant, and a lot of you probably didn't even know it was a measure of concentration. Never worked. So, we talked about mixtures a long time ago. We said there are homogeneous mixtures and heterogeneous mixtures. We're going to break those down a little bit more and use some other terms for them. First of all, we have a suspension. Okay, a suspension is essentially a heterogeneous mixture. It is some stuff floating in a liquid. If you let that sit, it will settle out. Okay? It's visible, you can see it, they're big particles, and if you let it sit, they will settle out. If you make those particles small enough, you get what we call a colloid. A colloid is essentially clear. It's like you can't even see the particles, but they are there. They're not dissolved. Okay, we'll talk about what we mean by dissolved. But in a colloid, they are not dissolved. They are particles floating in the liquid, just like a suspension. They're just very, very small. And they're so small that they don't settle out. Colloids are not common. Okay? That's not something we'll have in lab. They're not something we'll talk about in real life. Because in most cases, we don't come across colloids. We do deal with solutions a lot. In a solution, there are no visible particles. Everything is completely dissolved. When we say dissolved, we mean that it is broken down into individual molecules if it's a covalent or molecular compound. If it's an ionic compound, the ions are broken apart. Okay? In this case, if this is water, the water would grab those molecules and pull them all apart. If you have a chunk of sugar, the water would grab all the sugar molecules and pull them apart. The water would grab the sodium chloride and then pull the ions apart. Okay? In that case, every single molecule or every single ion is floating around independently in the water. Solutions are generally something like this. That is what we think of when we think of solutions. Something dissolved in water. In this case, this is just saline, sodium chloride dissolved in water. But technically, a solution does not have to be a solid dissolved in a liquid. It can be a liquid dissolved in a liquid. In this case, this is actually gas dissolved in a gas. Air is a type of solution. A solution can be one type of gas dissolved in another gas. So here, if you're giving oxygen to a patient, you don't give them straight oxygen. You give them something that's closer to normal air. And so there's going to be nitrogen in there, and there's going to be some CO2 in there. You can also have solid solutions. Has anyone ever had screws put into a bone? Couple. They still in there?
Yeah.
A lot of times, nowadays they're titanium, but they are not 100% titanium. They need to tweak the properties of titanium just a little bit so that they get something that is medically useful. And they do that by adding small amounts of some other metals. In this case, they added a little bit of aluminum and a little bit of vanadium. When you do that, you can really get your metal to be exactly how you want it. Even though this is solid in a solid, this is still a solution. Okay? Just keep in mind, even though solutions generally, when you look at them, are liquids, technically they do not have to be. So a solution has a couple different parts. Okay? The solution itself is a homogeneous mixture. Okay? That is our definition of a solution. In that mixture, we have a solute and a solvent. The solute is the thing that is being dissolved. In most cases, certainly in any sort of quiz or exam question that you would see, the solute is the thing that's going to be present in the smaller amount. If you mix two things, the one that there's less of is the solute. We say that is the thing that is being dissolved. And then the solvent is the substance that is doing the dissolving. It's the thing that there's the most of. So if you dissolve salt in water, water is the solvent, salt is the solute. An aqueous solution is just a subset of solutions where the solvent is water. So there are plenty of solvents. Pretty much any liquid can be a solvent. I mean, if you have something you need to dissolve, if you've got stickum from a price tag on a gift that you want to give, you're going to use something like rubbing alcohol to get that off. Rubbing alcohol is a solvent, okay? It's just a very different solvent than water. We'll talk about why later on, but there's a reason you need to use rubbing alcohol to get that stickum off, because water won't work. So this is something being dropped into something else. Looking at that picture, which one is the solute? The solid. The solid is the solute, and what is the solvent? The liquid, which is probably water. We talk about solubility. And solubility is how easily it is to dissolve a solute in a solvent. In every pair, a given solute and solvent will have a certain solubility. An ionic compound, remember, if you dissolve it in water, will break apart. Most ionic compounds are very soluble in water, meaning that they dissolve in water very well. What we call an insoluble compound is something that does not dissolve. In that case, they would just sort of sink to the bottom of your beaker and sit there in the same crystals that they were when you dumped them. As you remember from the solubility tables that we've used for double displacement, you can't necessarily predict the solubility. People just tested them all. They took a little bit of this, a little bit of that, put it into some water, saw how well it dissolved. So this is the solubility table that we had in our lecture slides a while ago. There are some similarities, but you can't look at the periodic table and predict that silver, mercury, and lead won't be soluble with chloride, bromide, or iodide, but everything else will. There's just no pattern to that. So in order to predict solubility, you need to look at the table. We can do a number of things to change how fast something dissolves. Without looking at your slides, what can we do to make something dissolve faster? Heat it. What else? Mix it. Those are the two easy ones. And can anyone get the third one? The third one's more difficult. That probably just heat it up. Okay. So we've got temperature. You ever tried to make Jell-O without heating it? It's not going to dissolve very fast. You're going to be mixing a long, long time. We can change surface area. Surface area is the third one. If you're putting sugar in the water, what do you think is going to dissolve faster? Granulated sugar or a sugar cube? Granulated. Why? It's smaller, it's more surface area, but what does that actually cause?
Well, the water molecules, if you have just a brick, it's only hitting the sides.
Exactly, exactly. The water can only dissolve the part of the sugar that it's touching. If you have a cube of sugar, you can only dissolve what's on the outside of that cube. Once you dissolve that, then you get what's inside. But you slowly work your way in. If you take that and break it up into this, you have a whole lot more sugar that's actually touching the water. And so you can dissolve a lot more at once, at the same time. And the last one is mixing. When you were a little kid and you were making Kool-Aid, you probably didn't think ahead and say, I'm going to want Kool-Aid tomorrow, so maybe I should make Kool-Aid now. When you decided you wanted Kool-Aid, you wanted Kool-Aid. And so you didn't just dump the packet in the water, put it in the refrigerator, and come back. You had to mix it. If you just dumped it in there and put it in the refrigerator, it would take a long time to dissolve. So you mixed it. Mixing is the third thing that we can do to make something dissolve faster. That takes us to our electrolytes. So we learned about electrolytes in lab last week. What is an electrolyte? It's essentially an ionic compound dissolved in water that will cause it to conduct electricity. Okay? Where did you hear the term electrolyte a lot? Sports drinks. Thinking back to what you did in lab Thursday, what can you tell me about how common electrolytes are? They're very common. What is an extremely, extremely common electrolyte? Salt. You can put salt in water and call it an electrolyte drink. Okay? Electrolytes are just a fancy word that they put on there to make it seem scientific. Okay? For us, an electrolyte is a solution that conducts electricity. And there are two types. We had the strong electrolytes, where the ions were completely dissociated. These were our ionic compounds. The ions are completely dissociated, so they're strong electrolytes. They're strong electrolytes because since they completely dissolve, there's lots of ions floating around. Our weak electrolytes were compounds that only partially dissociated. Only some of them actually broke apart into ions. Do you remember an example of one of those that we had? What happened with the acetic acid? Do you remember? We had two types of acetic acid. The diluted one was weak. Acetic acid is a weak electrolyte because only some of the molecules will have the hydrogen break off. If only some of them have the hydrogen break off, you don't get nearly as many ions as are possible, and so it doesn't conduct electricity nearly as well. And then something that doesn't break apart at all, what was an example of a non-electrolyte that we had? Say it again? Distilled water was a non-electrolyte. Why is distilled water a non-electrolyte? Because there's no ionic bonds. What did we dissolve in water, but that was still a non-electrolyte? CO2 was, but we didn't measure that directly. Sugar. Molecular compounds. A molecular compound is going to be a non-electrolyte. So if you see a question that says, which of these is an electrolyte? How are you going to tell?
Which has ionic bonds.
Which one has ionic bonds? So you're going to pick out the one ionic compound. If the question said, which of these is a non-electrolyte? You're probably going to look through and all of them are going to be ionic except the one. So you pick out the one that is different than all the others. Like you saw in lab, you can test for electrolytes with a light bulb. It's a much bigger light bulb with a much bigger battery than you had. But if you put hydrochloric acid, it breaks apart into chloride ions or hydronium. Sodium chloride gets sodium chlorine, nitric acid dissociates, sodium hydroxide dissociates. These ions can move around. They can move from one pole to the other, conducting electricity from one side to the other. Like we said, molecular compounds or covalent compounds are non-electrolytes. If we take hydrogen peroxide, pure hydrogen peroxide is a liquid. Okay? The stuff that you buy at the store is not pure hydrogen peroxide. But hydrogen peroxide in pure form is a liquid. If you dissolve it in water, it is still H2O2. It does not break apart into ions. Hydrogen peroxide is a molecular compound. So even though it's dissolved in water, it is still H2O2. We just go from liquid to aqueous. So, we're going to look at these compounds. We're going to figure out whether they are electrolytes, weak electrolytes, non-electrolytes, and we have to write an equation for what happens when we dissolve them in water. So the first one on our list is zinc chloride. If we dissolve zinc chloride in water, what's it going to turn into? Zinc ions and chloride ions. So we take zinc chloride solid, we dissolve it in water, and we get zinc ions plus chloride ions. Is that correct?
Oh, no, it's not balanced.
It's not balanced. What do I have to do?
Let's put it to chlorine.
We started with 2 chlorines, and so we get 2 chlorines. Once it's dissolved, those 2 chlorines are completely independent of each other. And so they are 2 chloride ions. They go their separate ways, and so you have to use 2 as a coefficient. What about potassium nitrate? We dissolve that in water. What are we going to get? Potassium ions and nitrate ions. So we've got KNO3, solid. Dissolve in water, we get potassium ions, NO3 ions. Is that correct? Yes. What about that last one? C2H5OH. That is ethanol. So we've got C2H5OH liquid. We're going to dissolve it in water. It's going to stay ethanol. So we still have C2H5OH. What is the state? It's still it's aqueous. Just like the ions are. It's now dissolved in water, so it's aqueous. But it didn't break apart. Why did it not break apart?
Hydrogen bonding.
It has hydrogen bonding, but that's not why it didn't break apart. There's no ionic bonds. This is a molecular compound. Molecular compounds don't break apart. So we talked about three things that will increase the rate at which something dissolves. But there's always a limit to how much you can dissolve, right? If I have a beaker of water, there's only so much salt that I can dissolve in. At some point, the salt is going to stop dissolving. And there are three things that determine how much of something will dissolve in our liquid, in most cases, water. Okay? The first one we'll talk about is structure. It simply depends on what the solute is. Some things are more soluble in water than other things. We've also got temperature. Temperature is the one you're most comfortable with. What effect does temperature have on the ability to dissolve something in water? It makes it faster, but do you know what it does to the ability to dissolve a total amount? Can you dissolve more in hot water or less? More. You can, in most cases, you can dissolve more of a solid in hot water than you can in cold water. And then the last one we'll talk about is pressure, and that only applies if you're dissolving a gas in a liquid. So the first one was structure. These are two vitamins. We have vitamin A and vitamin C. Okay? Have you heard the terms fat-soluble vitamins and water-soluble vitamins? This is what they're talking about. Okay? Based on experience, or by looking at up here, do you know which one is which?
A is fat, C is water.
Yes. Do you know that from experience, or by looking at that?
Nutrition.
Okay. Does anybody know by looking at this? I'd be surprised if you did. Okay. So vitamin A is a fat-soluble vitamin. Vitamin C is a water-soluble vitamin. Looking at these two structures, okay, we've got the carbons, single bonds, double bonds, hydrogens, all around. This is how you draw molecules in organic chemistry. This is not something we're learning, but I think you can probably look at this and get the gist of it. We have different atoms bonded singly or doubly to other atoms. What can you tell me about the difference, this very superficial difference between the two?
One's quantum, one's long.
What do you mean by clock?
Like it's all condensed together. It's not longitude.
It's much smaller, right? And so, I mean, essentially, on both of them you have this kind of the same CH3 with an O, and then do you see the same thing on the end of each?
Yeah.
You see that? And then on the left end, you have a ring. I mean, that's a 5-membered ring. This is a 6-membered ring. But on the left-hand side, we have a ring. And then in between them, on this one, we have a whole bunch of carbon-to-carbon bonds and carbon-to-hydrogen bonds. What can you tell me about a covalent bond that's between a carbon and another carbon, in terms of polarity?
They should be the same.
They're non-polar bonds, right? Because if it's the same element, they have the same electronegativity. And so a bond between them will be non-polar. And what is special between a carbon and a hydrogen atom? Carbon and hydrogen was actually the one exception. Carbon-hydrogen, even though they're different elements, is still non-polar. So, on this vitamin A, from about here over, every single bond is nonpolar. You see it? The only polar bond we have is that one and that one. Everything else is nonpolar. When we look at this one, we have the same polar bonds here, but there's a whole bunch of other oxygens here making a whole bunch of polar bonds. And so this has a lot more polar bonds than nonpolar bonds. This one has a lot more nonpolar bonds than polar bonds. So this is a nonpolar molecule overall. This is a polar molecule overall. What do you know about the polarity, that may be nothing, of fat in water?
That's non-polar.
Fat is nonpolar, water is polar. And so the polar vitamin dissolves in water, which is polar. The nonpolar vitamin dissolves in fat, which is nonpolar. This is fat. It's a triglyceride. So you have this backbone here, this carbon backbone, each with an oxygen, sort of serving as a linker. And then you have these big, long carbon chains. And so even though in this end you have some oxygen that makes this end of the molecule sort of polar, the vast majority of the molecule of fat is nonpolar. And so fat as a whole is nonpolar. And so the nonpolar vitamin A will dissolve in the nonpolar fat. Why do you think water and oil don't mix? They're opposite polarities. Which one's which? Oil is nonpolar. Water is polar. Oil is basically fat. I mean, this is petroleum oil, but vegetable oil is still oil. Vegetable oil is basically fat. Okay? And really the only difference is fat is room temperature, is solid at room temperature. Oil is a liquid at room temperature. If I take carbon tetrachloride, CCl4, and I mix it with C6H14, which is hexane, they dissolve in each other. Why? What can you tell me about polarities?
Because
They're both nonpolar. And so even if you didn't know whether they were both nonpolar or both polar, they must be the same. They're either both polar or they're both nonpolar. Otherwise, they wouldn't dissolve in each other. And that's what we mean by soluble in one another. Imagine drawing the molecular shape of CCl4. Even though those bonds are polar, it's symmetrical. So CCl4 is nonpolar. Hexane is a six-membered ring. Six-membered ring with a carbon on each corner, and then coming off each carbon are two hydrogens. So, number one, it is completely symmetrical. I mean, it's the definition of symmetrical. And all of the bonds are nonpolar. So either carbon-carbon or carbon-hydrogen. So that is very, very nonpolar. Since they're both nonpolar, they'll dissolve in each other. What about oil and vinegar? If you're one of those artsy people that has the little vase on your kitchen windowsill of the oil and the vinegar, it looks like that, all right? They don't mix together. Why?
you have a molecular compound and the non-molecular.
Well, That's the oil, right? Oil we said was non-polar. What is vinegar? What is vinegar? I mean, think even.
Liquids.
It's acetic acid, which is what? I mean, remember in lab we had concentrated acetic acid and 0.1 m acetic acid. Which one is vinegar? We had two forms. It's the diluted one. Okay? When you have a bottle of vinegar in your closet, it is mostly water. Okay? There is some acetic acid dissolved in it. So essentially, we have oil and water. And you know that oil and water don't mix. That leads us to the little phrase, like dissolves like. Polar solvents dissolve polar solutes. Non-polar solvents dissolve non-polar solutes. And so, non-polar solutes are going to be molecular compounds. Molecular compound that is non-polar is going to be here. It'll be soluble in non-polar solvents. A polar molecular compound is this. It is soluble in a polar solvent. Ionic compounds are very, very, very polar, so they're soluble in polar solvents. So if you're trying to figure out if something will dissolve in a solvent, figure out whether they are the same. If they're both polar, they will dissolve. If they're both non-polar, they will dissolve. If you have one of each, it doesn't matter which way you go, whether it's a non-polar solute in a polar solvent or a polar solute in a non-polar solvent. So if there's a mismatch, they won't dissolve. Here's two compounds. I guess that's not a compound. Here's two molecules. Which one would you expect to be more soluble in water?
Yeah. No.
Ask yourself this. What is the polarity of water? Polar or non-polar?
It's polar.
Polar. And so essentially what this question is asking you is which of these is polar?
So then the one on
Yeah.
This one. This one is polar. That is two atoms of the same element bonded together. So that is symmetrical and it's a non-polar bond. And so this is as non-polar as you can get. This is not going to be symmetrical. So this is more soluble in water. That is actually methanol. Methanol dissolves in water very well. Which of those two would you think is soluble in benzene, which is a lot like hexane, but there's alternating single and double bonds?
What did we say that which one should be more soluble in water?
Methanol. Which one would be more soluble in benzene? The iodine. This is non-polar, and so the iodine is non-polar. So the iodine is soluble in benzene. We said that changing the temperature will change how much something you can dissolve in your water. That is in most cases. There are some weird examples where changing the temperature of your water actually won't change how much of your solute you can dissolve. And oddly enough, one of those weird examples is salt. Most ionic solids are more soluble in water at higher temperatures. Okay? You don't need to really worry about the exceptions. If you remember, solids are more soluble in hot water, you'll be good. Okay? Where it gets tricky is gases go the opposite direction. Gases are less soluble in hot water. Okay? This is a chart of increasing temperature in how much of each different gas we can dissolve in water at that temperature. So as we go to higher temperatures, the amount of oxygen decreases really, really quickly. So around here, our lakes are really shallow. And so when it gets hot, what happens to the amount of oxygen that's dissolved in the lake? It goes down. And around here, it stays hot for 6 months out of the year. So if the water level, if we get a drought, and the water level, even though it starts shallow, keeps dropping and dropping and dropping, the fish don't have anywhere to go where it's cool. In deeper lakes, they can go down where it's deeper. Where it's cooler, there's more oxygen there. Here, they don't have anywhere to go. And so you can get fish kills, where a good portion of the fish in the lake die simply because it got so hot that the oxygen couldn't stay in the water any longer. Okay? Any bass, a lot of people in here fish. We've talked about that the first day. Any bass fishermen? Any tournament fishermen? Okay. Do you ever fish summer tournaments? Do you ever fish summer tournaments? If you fish a summer tournament around here, well, if you're not familiar with bass tournaments, you don't kill the fish, but you have to keep them with you to weigh them in at the end. You have to bring your five biggest in to weigh, and whoever has the most weight at the end wins. Okay? You get penalized if the fish die. Okay, it's a conservation thing. And so you have to keep the fish alive. Once you catch the fish, you put them in what's called a live well. It's basically a little aquarium built into your boat. Okay? But it's about that big. Imagine that on 95-degree Florida day in the sun. It gets really hot. There's not much water in there to begin with, and so you have a limited supply of oxygen for the fish. If it gets so really hot, all the oxygen comes out of the water and your fish die. And so in the middle of the summer, people will take coolers of ice with them, and they're constantly putting ice into their live wells to keep the temperature of the fish down. One, that keeps us down here, so there's more oxygen dissolved, but also slows down the metabolism of the fish. So the fish are using less oxygen. If you don't do that, you're probably going to kill all of your fish. So that is literally how I remember solubility of gases in water. I think about, I have to put ice in my live well to keep the oxygen in the water. That is literally my thought process when this question comes up. Okay? So if you can remember, gases are opposite solids. Okay? That's great. If you have to come up with an example to let yourself work it out in your head, that's great. Another way to think about it is, you have gases. Gases want to be gases. When you heat something, it tends to want to be a gas. It evaporates faster. And so you can think of it as, if you heat that, you're going to drive the gases out, because they want to be gas, not dissolved in the water.
Oh, I was going to say, like, is it kind of like related to surface area, kind of like, because as gas gets higher in temperature, its speed makes sense.
The amount of surface area will change the rate at which you can exchange gases. So if you have a glass of water like that, to get the oxygen in the water, it has to go through that surface, right?
Yeah.
If you have a big dish of water with the same amount of water, you have a much larger surface area for the oxygen to come in. If you have fish in here, the fish are making ammonia also. The ammonia has to be able to get out. And so a large surface area will allow the ammonia to get out. Whereas here, you only have a small amount of surface areas. If you're dealing with gases, the pressure of the gas will also dictate how much of it gets dissolved in your liquid. Okay? With complete logic, if I have a container, let's say it's a sealed container, and I have some water down here, and then I have gas up here. Do you think high gas pressure here is going to make more dissolved in the water, or low pressure up here is going to make more dissolved in the water? You got one low.
It goes from high to low.
When we say pressure, think of pressure as pushing. Remember, in our balloons, if the pressure pushes on the inside of the balloon, pushes it out. In this case, you can think of pressure as essentially pushing this gas, pushing these molecules down into the water. High pressure, those molecules are trying to go somewhere else. They want out. And so they're going to push it down into the water. Another way to think about it is if you have high pressure, you have more molecules up here. That's what's creating the higher pressure. If you don't have nearly as many molecules, in order for the gas to dissolve in the water, it has to hit the water. And so if you have fewer gas molecules flying around, fewer of them are going to hit the water. So, high gas pressure increases the amount of gas that dissolves in a liquid. You're the scuba guy. Does this ring a bell in scuba for aquatics?
Could you explain it?
Yeah, we'll get to it. So this is essentially what we had here. This is our piston system with a liquid and our gas. If we push down on that piston, the pressure of our gas goes up because our volume decreased. So our pressure goes up. So essentially, we'll push some of that gas down into the liquid. Okay? This is what happens with your soda bottles. You ever wonder how they got the soda carbonated in the bottle? No?
Yeah.
Yes, thank you. When they bottled it, they did it at a high pressure. And so they had the soda with a very high CO2 pressure, which made a lot of the CO2 dissolve in the soda. They then capped it. And so even though we have low normal pressure out here, in that little gap up top is a very high pressure of CO2. What happens to the pressure at the top of the bottle when you take the cap off? It decreases. It goes back to atmospheric pressure, normal pressure. All of a sudden, we have lower gas pressure. If we have lower gas pressure, the gas isn't as soluble in the liquid. And so what happens? It fizzes. We get little bubbles. The bubbles are the gas coming out of solution. The solubility is now lower. It has to go somewhere. So you get bubbles that form, float up, and then the CO2 escapes. How can you keep, if you have a 2 liter, and you want to use it multiple times over a couple days, how do you keep it from going flat? Put it in the fridge, put the top on. What happens when you put the top on? It contains the CO2. All of a sudden the CO2 can't escape. And so you rebuild this high pressure up here. And once you rebuild the pressure, the CO2 stops coming out of solution. If you take up your bottle, and before you put the cap on, you squeeze it, and so you minimize the amount of space up here, you minimize how much CO2 has to bubble out in order to fill it. No, if you squeeze it, it saves just the CO2. Because imagine you have a bottle that's half full. If you just put the cap on, you have to get enough bubbles to fill half a bottle. But if you squeeze it, and so the Coke is about to come off the top, then you put the top on, you have this little tiny space, you only need enough bubbles to fill that much space.
So when you shake it, why is more CO2 released?
That is, in order for the gas bubbles to form, they need something to form on. Okay? We'll see that in a minute. So when you shake it, you get this little bit of CO2 forms of some bubbles, right? Once you give those bubbles get those down here, these bubbles form on those bubbles. So it happens a lot quicker, and generally shaking anything makes it happen faster. You're essentially mixing, and mixing always makes things happen faster. So, yes, that's scuba diving cat. Scuba divers deal with this gas pressure versus solubility issue all the time. If you're scuba diving deep, what can you not do?
You
can't come up.
You can't come up fast.
You have to make, I've made deep like 150-foot dives. You actually have to come up to a stopping point and wait.
Right. And so, based on what you feel in your ears, is the pressure higher at the surface or down below? It's certainly. You don't have to go down very far at all to know that there's a very high pressure as you go down in the water. So as you go down, the pressure gets higher and higher. As you go deeper and deeper, what's going to happen to solubility of gases in water? Pressure's going to go up, so the solubility goes up. What in your body is mostly water?
Your muscles.
Your muscles. What's something that goes through your body that is blood? So, we breathe in oxygen, we breathe in nitrogen, we breathe out CO2, right? All of those things will become more soluble in your blood as you go down. That's fine. If it's dissolved, it's dissolved. Who cares? Where the problem comes in is when you come up. You have to come up slow. What would happen, do you think, if you went down, all of that gas dissolved in your blood, and you came up really quick because a shark bit your foot?
Your eyeball would come out.
Probably not that.
It's bad, but I've seen videos.
The gas tries to escape it.
The gas tries to escape. Right. So think about it in chemistry terms, not eyes bulging out of your head terms. Okay?
Oh my gosh.
As you come up, that pressure goes back down. As the pressure goes back down, the solubility decreases. And so, this happens in your blood. That's not good. Why is bubbles in your blood not good? Well, it's mostly nitrogen.
Forms blood flow.
It essentially acts like a blood clot. Imagine you have a hose and you get a big air bubble stuck in it. The water, your blood, can't get past that air bubble anymore. Okay? So our body are full. If it's in an artery, a giant artery, it's not a big deal. It's just the bubble's going to go through and your blood's going to come behind it. But if that bubble gets in this tiny little capillary, it has nowhere to go. Capillaries get smaller as they go out. And so that bubble is just going to get pushed in and no oxygen is going to get past it. Also, your heart is a pump. What happens when a pump loses prime? It doesn't pump anymore. And so if you get a big bubble, it gets to your heart, you die. That's called an embolism. That's not good. And so, if you come up really fast, there's a term for that medical condition. What is it? The bends. Does anybody know what you do to get rid of the bends? You go in a hyperbaric chamber. What does that accomplish?
Higher pressure.
You bring your solubility back up. Yeah. And so the hyperbaric chamber is very high pressure. And so it increases the solubility of the gas back to where it was when you were at the bottom of the lake. And so the bubbles redissolve. And then you can very slowly decrease the pressure in the chamber to simulate coming up very slowly. And so you take the bubbles, you redissolve them, and then you bring the pressure back down slow enough that instead of bubbles forming, you just exhale the gas as it comes out of your blood.
You know, by the way, it's funny that you mentioned if you get bit by a shark, because of my dive instructor used to say, like, this is like when I first got certified when I was like 12, he's like, you have a better chance of living off fighting with the shark than like.
Oh, I would imagine, yeah. Bends is bad. And Yes, I see no reason a cat can't get the vents, if you're wondering. Although, you've never scuba dived with a helmet.
I haven't done it.
I would guess the helmet probably has a pretty good air pressure. It probably maintains a normal
I know
pressure.
they're expensive. They're like a few $1,000. The communication helmets. But I've
The
never-
cat version or the human version?
Well, they have human versions. But they're expensive. You know, I'm sure it's the same kind of system. I'm sure it's like a few $1,000.
My question, where do you get that? Because I mean, that's like baby size. And who buys it, takes their baby scuba diving?
That cat really in the water.
Certainly looks like it.
That's more.
Looks like it to me.
Photoshop. Yeah.
Okay. We have to measure the concentration of our solutions. We now know what the solution is, but we have to measure the concentration of it. What do you think I mean by concentration? How much solute is dissolved in the solvent? That's what it means. Okay? That's what that 0.1 m was telling you. It was telling you the concentration of those solutions. Concentration is how much solute there is in your solvent. A saturated solution. Now a definition. A saturated solution means you have the maximum amount of solute for the solvent that you have. You have reached that solubility limit. You've dissolved until you can dissolve no more. Okay? That is a saturated solution. An unsaturated solution is below that limit, meaning there is some dissolved, but you can still dissolve more. And then, what solubility is telling us is how much is the concentration that is that limit. So solubility will be described as something like grams of solute per grams of solvent. And so you could say that solubility of sodium chloride is, let's say, 50 grams of sodium chloride per 100 grams of water. So that means a saturated solution at the limit, if you had 100 grams of water, you would have 50 grams of sodium chloride. If you had 200 grams of water, that's double what's given. You would have double 50, so 100. Okay? You can also have a supersaturated solution. Supersaturated solutions are essentially rebels that don't follow the rules. Okay? There's a certain set of circumstances where you can go beyond that limit, where you can actually have more solute dissolved in your water than that solubility limit says you can. And it has to do with the fact that for something to come out of solution, if you have a solid dissolved in water, for it to come back out of solution, it has to form crystals. And when it forms crystals, it needs to have something to form the crystal on. Just like the bubbles in your soda had to have something to form a bubble on, the crystals have to have something else to form a crystal. Once you have a crystal, then everything else can form on top of that crystal. If I take this flask and I heat the water up, and then I dissolve a bunch of, let's say, sugar in the water. Because it's hot, I can dissolve a lot of sugar in it. If I let it sit there, it's going to cool. When it cools, what happens to the solubility of the sugar? It goes down. All of a sudden, I can't have as much sugar dissolved in that water. That sugar needs to reform crystals. But if the inside of my flask is completely smooth, and I don't jostle it, I don't do anything, the sugar can't reform crystals. But that doesn't mean the water is going to stop cooling down. It's going to cool down to room temperature no matter what. If you then take what we call a seed crystal, just a little bit of something, and you drop it in, all of a sudden you now have something for the crystals to form on. And so you can get crystals forming, and you get more and more and more, until enough comes out of solution that you get back down to that limit. And then your crystals stop forming. Has anybody ever made rock candy? This is what you did, right? You took sugar, dissolved it in water, added some food coloring, then you probably put a string down into it, and then you let it cool. The string was acting like a seed crystal. It was a surface for the sugar crystals to form on. And so you dissolved the sugar in the water, and then it came back out of solution onto your string. And then you had candy.
So that's super saturated?
It was super saturated.
Yeah, what form?
It was super saturated as it was cool. And so because it was super saturated and you had a surface there, you were forming crystals. When you heated it and dissolved it, while it was still hot, it was just saturated. But then as it started to cool, it was super saturated. In organic chemistry, one way that we purify something that we make. So we make a solid, it's in crystal form. We get impurities in it. We actually will, what we call recrystallization. We'll dissolve it in a solvent, hot solvent, and so we can then let it cool and get our crystals back. When we do that, we get a supersaturated solution. We can either add a seed crystal, that would work, but we don't want to do that. Why? Why do you think? If the goal was to get as pure of a compound as possible, we don't want to add something else to it. Because usually the seed crystal is a little bit of the original unpure stuff that you saved back so that you can drop it in to get this. But that's going to have some contamination in it. So what we actually do is we take those glass rods that we have in lab, you've seen them, the little skinny, look like glass pencils, and we'll take it and we'll scratch the bottom of the glass. And we get this tiny, tiny little scratch that creates a little surface to form that. So this is what we call a solubility curve. This just shows how much of something can be dissolved in your water at a given temperature. Okay, this isn't a curve or graph that you would ever have to read, but it just shows what we've talked about. Okay? As you increase temperature, solubility of sugar goes up. But salt is that weird exception. Salt doesn't really change its solubility with temperature. You can't really dissolve more salt in hot water than you can in cold water. So this is an example of how we would use solubility. So this says solubility of salt is 38 grams in 100 grams of water at 25 degrees Celsius. Okay? We make a solution. So this is out of a book. The book tells you it's 38 grams of salt in 100 grams of water is your limit. If we make a solution that is 45 degrees or 45 grams of salt in 150 grams of water, is it unsaturated, saturated, or supersaturated? Now, there are a couple ways that you can do this. How do you want to do it? There's no right or wrong way as long as you get to the right answer. So what is one way that you see we can do this? Let me walk them through what I think you said. Okay, because I think if I understand what you said, you're correct. Okay, so you said we have 150 grams of water, which is 1.5 times that much. Okay, and so half of 38 is 19. And so if you have 1.5 times as much water, you can dissolve 1.5 times as much salt. And so 1.5 times 38 is 38 plus 19, which is 57. And she said is you should be able to dissolve 57, but you only dissolve 45. Is that what you said? Okay. So, if that's the case, is it unsaturated, saturated, or supersaturated? Unsaturated. You are below the limit. Okay? That is how I mentally do that problem. The same way she did.
I applied I don't know if it's the same thing. I divided 38 by 100 to get the ratio,
Yep.
and then I saw the difference in the new ratio.
Yep. That is the other way that I see to do it. And so you can just compare the ratio of salt to water in both of them and see if your solution is higher or lower than that limit. So if you go 38 divided by 100, you get 0.38. If you take 45 and divide it by 150, what does that come up to? 0.3. You get 0.3. In this case, you have to be able to look at this and figure out, okay, they're different, but what does that mean?
8%.
So in this case, because you have the salt on top, the higher that number, that means more salt. And so if 0.38 is your limit, you're below that limit. Does that make sense? So the book gives you the limit, figure out that ratio. Calculate your actual ratio, and if you're below the limit, you're below the limit. That's unsaturated. Make sense? I think this is a good place for a break. Let's start again at 7:30.
Can you go back to that slide you just did? Okay, I just wanted to see the answer.
It is correct.
I mean, it makes sense, but if this is 57, that's 40, that's 38. If 24 divided by 2 is 19, 19 plus 30.
No, I mean, like, I live in my mom's house, so my dad lives here in Gainesville.
I have a question.
What kind of work does she do?
To me, I don't get it this way.
Are you still?
30 divided by 2, 19 plus 38, 27. You have to divide that all in.
In this case, this is the first method. And so what this is saying is, if the limit is 38 to 100, what you just figured out is the limit that you can dissolve 57.
It's for my grandpa.
That's what that's telling.
That's when he died.
So what's the 25?
That's just saying, because the solubility could change with temperature. And so a solubility is going to have a temperature associated.
But if it's, I don't understand how it's unsaturated if this is, if this number is more than this number.
This is the limit, this is what you actually
So I
have.
made it a heart.
Oh, so
So
I'm
you're
finding
below
the
the
limit.
Right.
I have a quote on my shoulder.
And so because
My heart always on
the
mine.
limit they gave you was per 100 grams. So what you essentially did is you adjusted that limit to reflect 150 grams of water.
Okay. So I'm finding the limit and I'm making sure it's below or above.
Correct. So you adjusted the limit so that you can compare apples to apples.
Why?
You
I don't
compare it
mind.
to what
It's just
actually
like
have.
it's a tiny little sun. I'm like, whatever. Really? And my performance is really high. Like I was like, you know, I'm supposed to
If your question is at one point in time.
It's not even moving. It's
So she can fill up her truck.
Anything is changing.
How do you send that?
Huh?
How do you
It's a
send
big
that?
one.
What's their new
P1,
one?
D1 over N1, D1.
Really?
We actually learned this mind gap through.
When I said that, I was only gonna be washing up.
Oh my gosh.
Anything
Probably
that
wash
changes.
like one load a week. How much do you want?
If one of
Oh
these
my
variables
goodness,
is
that's
installed in the
so
problem, you should raise it. But if N is not involved, then or if you have a problem where volume is involved, you set the other three up. And so the 18, so the combined, the thing is changed, right? The bottom of the plate, these are changing. Then you immediately go to combine it, not like, then nothing's changed. It's like you have a tank. I know this is how much it is, how big the tank is, temperature. That's not changing.
Compared to chips. Yeah.
No, it's actually pretty good. Yeah, I get perfect. So. Oh, is that how that works? Okay. Make sure I get that next time. I do it for myself. No? One meal a day. Oh, but oh, wait, you said that earlier? Wait, why did you know am I supposed to? Oh, okay, then okay.
Sorry then. Broke me one from semester of last semester. So I went to go up and get a green one.
You guys actually work on that? No, how do you do that?
No, it's not
Right? Yeah, and her baby is due the day after Mother's Day. Yeah, I know. I think Mother was pacing. Are we about to go to the homework? See that 3 out of 3? See that 3 out of 3?
You're safer in here.
That's very like.
Neutral? How did you, I'm like, what?
Idle.
Neutral.
And then I'm like, see how I jump the ship? Just like, this is going on. Then I look down at my gears already. Check my car.
Maybe the rain's like not too good to show up in so.
Brings all the leaves.
I have like 3 in the back of the car. Yeah.
Oh my God,
Like I was collecting from work, I could probably leave the umbrellas and leave them for like 3 months and I'm great.
No, this
I know.
we have a turn in the clothes like this too. This Thursday.
My last assignment, I had a trip assignment. So, I was scared to watch it. I was like, no, go away. It was like covered in marker. Yeah.
Oh, you was in the washing machine?
It doesn't.
Yeah.
I thought you just meant like.
No,
No, right?
I would have had one.
She said, you're like, what are you trying to do?
I'm not trying
Huh?
Sharpie? Yeah, Sharpie on my lab coat. No,
You gonna have to start?
but I don't want to wash it.
I might have to.
Shut up.
You don't wash that thing?
Not even like 40 hours.
Dude, I literally wear like
I'll
less
put
than
40 hours. Can you tell your
No,
40 hours.
we have a wall of lab. It's like 60 degrees in there.
You get paid 1040 now.
Do we have a wall of lab?
Not a lot.
Huh?
Oh, that day it's happening.
Is there audio?
You gonna crop it out?
Stressed out about the rain.
Did you swear on it?
No. Talking about music.
Is it something really that
No.
needs to be?
Okay.
You don't cut
But we
that
can-
out.
Huh?
Like when we go on break, we don't cut that out anyway.
Well, no. But then I'd have to,
It's just a long bit.
I'd have to go through the process of editing it and editing it. My suggestion is not to
You're
say
not
something you
gonna-
don't want on there.
You about to get hit. She's trying to hit you.
Oh my goodness.
I thought she was gonna like fall out of her chair.
Right, we just have
Okay, so, as with pretty much everything we do, we have to put numbers with them, okay? So if we talk about concentration, we have to have not just saturated, unsaturated, supersaturated, we have to have numbers that go with it, okay? And there are a lot of different units that we can use to express concentration. We're going to go through quite a number of them, okay? But the one you need to know is the molarity one, okay? So we'll go through them. The first few, yes, they're good to know, but they're not as important as the molarity. Okay? So we have percent by mass, percent by volume, mass per volume, parts per million, parts per billion, molarity, and then molality. Okay? So that is our big one. So percent by mass of solute is really easy. It is mass of solute divided by mass of solution. So if I have 100 grams of solution and I have 30 grams of solute, I have 30% by mass of solute. It's just the mass of your solute, how much of what you're dissolving, divided by the total mass of the solution, the water plus the solute. That's all it is. So, we're making acetic acid, we're making vinegar. It says it contains 2.70 grams of acetic acid and 122.8 grams of water. How do we find the percent by mass of acetic acid in the solution? 2.70 divided by 122.80. Is that correct? Anybody say no? You have to add them. What's on the bottom is total mass. And so it's 122.8. 2.8 plus 2.70. Make sure you get the total on the bottom. So what does that come out to be?
2.1.
125.5.
Everybody say it again.
125.5.
125.5. And so what is this mass percent?
Oh, I thought you wanted the whole thing.
It's like
2.15%. And this is 2.15% acetic acid. Simple enough. Just make sure you add the total together at the bottom. Another one, mass percent of sodium chloride in solution, 10 grams of sodium chloride, 50 grams of water. So what goes on top of my fraction? 10.0. What's on the bottom?
10.0 plus 50.
So 60. Total. 10 plus 50 is 60. 1 divided by 6.
0.16 repeating 6 is
1666, which is 16.7%. And we've got percent by volume. Same calculation, it's just volume instead of mass. And so it's the volume of your solute divided by volume of solution. And you tend to do the masses if we are dissolving a solid in a liquid. If we're dissolving a liquid in a liquid, we tend to do percent by volume. Like if we want to dissolve ethanol in water, we would measure how much ethanol and how much water we have by volume. So on that extra credit question, I said I dissolve ethanol in water, sterilize things. That's 70% ethanol. To make that, I just take a graduated cylinder, I add 70 milliliters of ethanol, and then add water up to 100. And so there's 100 milliliters total, and of that, 70 was ethanol. That's 70% ethanol solution by volume. So in this case, we're dissolving 205 milliliters of ethanol to give us a volume of 235. We have to figure out the percent ethanol by volume. So what number goes on top?
205.
205. What number goes on bottom? 235. It already gave us the total. Why do you think it said insufficient water to give a total volume of 235? Why didn't it say plus 30 milliliters of water? Any ideas?
Do you have to have like pure water?
No, it's a matter of when you dissolve liquids together, two liquids together, the total volume isn't actually two volumes added together. When they dissolve, they kind of compact a little bit. So if you took 205 and added 30 milliliters of water, you would get less than 235. And so they say you take the 205 and then you just add however much water it takes. You actually never really know how much it is until you hit the 235 mark. Then you stop. That's what that's saying. Times 100. What percent is that? 87.2%. Capiche? Okay. We can also kind of mix the two. We can go grams of solute divided by the volume of solution. This is the lazy man's calculation. This is, I want to dissolve 30 grams of salt in some water, but I don't want to take the time to put the water on a scale when I can just read it off what it's already in. And so I know I have 100 milliliters of water, then we dump my 30 grams of salt in and see what the new volume is. Okay? And so here's an example. We have sodium chloride in a saline bag. If you're going to inject it into a person, it needs to be 0.9%. And so you can turn that around and say, for every 100 milliliters of solution, how many grams of salt are present? Using that formula, grams of solute divided by volume of solution, how would you calculate this? Multiply the volume by your percentage. And so essentially you have percent equals grams, or mass, let's say mass, divided by volume. We have three variables, percent, mass, and volume. Which is the one we're trying to solve for? Mass. And so we rearrange that. Mass equals percent times volume. And so mass equals, where's my percent? 0.9. Be careful when you put this in here. If you put 0.9, you're going to get the wrong answer. You need to put it in decimal form. That's in percentage form. So you need to divide it by 100. 0.009. Make sure you do that conversion. And then it's going to need to be in liters.
So 100,000.
Divide by 1,000. So how many liters is a milliliter? 0.1. 100 divided by 1,000, 0.1 liters. And so you get 0.009 times 0.1 equals 0.0009. And this is grams. Got that one? Now we got the big one, the molarity. This is what that M was on all of your bottles. 0.1 M means all those solutions with 0.1 molarity. And we say that as 0.1 molar. We just say something is 0.1 molar, or it is a 3 molar solution. A 3 molar solution means it has a molarity of 3. Calculate molarity. Molarity is a capital M. Make sure it's a capital M. It has to be capital. Equals moles of solute divided by liters of solution. This is another very important equation that is not on your cheat sheet. Okay? So you've got molarity equals moles over liters. So that's your equation. Molarity, the capital M, equals moles over liters. It's moles of solute, liters of solution, but what I get in my head is moles and liters, and the solute and solution work themselves out. So what's doing it? You have a solution that contains 117 grams of potassium hydroxide dissolved in sufficient water to give a total volume of 2 liters. It gives us the molar mass of potassium hydroxide. We want to find out what the molarity of our solution is. This is our equation. Which variable are we solving for? Molarity. So we need to find the moles in the liters and divide them. Are we given moles? No. So let's come back to that. Are we given liters? Yes. We're given the volume is 2 liters. We're not given moles. So how do we calculate this? Right. We're given mass, so we can convert it to moles. In a lab, you don't measure something out in moles. Your scale doesn't give you moles. Your scale gives you grams. And so we have 117 grams of KOH. We'll convert it to moles of KOH. What is 117 divided by 56.11?
2.09.
So now we have our moles. 2.09 moles. And so it's 2.09 moles KOH divided by 2.00 liters. 2.09 divided by
1.03.
1.0, how many? 36. So 0.5. And then this is molarity. So it's 1.05 molar, the capital M. If you really want to be complete, you can say molar KOH. But the KOH isn't all that important. The M is what's important. It's 0.45, which rounds up.
0.425.
No, it's rounded up on mine.
Because half of 9 is 4.5, which rounds up.
It's 1.0.
And so the answer, molarity of the solution is 1.05 molar. That one rounded down. What?
It's probably just because like the different.
It's just because it's 2.085 rounded. It's okay.
Oh, that what
Yeah,
it was?
yeah.
We rounded to the 9.
Yes.
Okay, thank you.
Yeah.
She's on top of it.
Yeah.
The problem with molarity is that if temperature changes, your molarity changes. Why? If I have a solution that's 1 molar sodium chloride, and I heat it up, why is my molarity going to change? What happens to things in general in terms of size when you heat them? They expand. Gases, we said, expand a lot. We didn't talk about liquids expanding because they expand just a tiny, tiny bit. But they do expand when you heat them. And so, if I have a solution, I have X amount of salt dissolved in there. My moles are not going to change. But if I heat it, my volume goes up. And so my molarity changes. And so people said, Well, in that case, I guess we can't use molarity all that often in the lab. Those people were gluttons for punishment. Molarity is very easy to use as long as you don't have big changes in temperature. The volume of your water is not going to change that much. You have more error in weighing out your solid, in measuring the volume in your graduated cylinder, than that volume is ever going to change. But because there were perfectionists around, they said, we can't do this. This changes. We need something that is not going to change. And so because they were, I don't want to say morons, but it's essentially what I mean. But they weren't thinking ahead. Let's put it that way, okay? And so, or maybe they were thinking ahead and they said, I want to punish chemistry students for the rest of time. They made something else and called it molality. Not molarity, but molality, okay? And the symbol is lowercase m. Capital M is molarity. Lowercase m is molality. And molality is moles of solute divided by kilograms of solvent. So the difference is molality uses kilograms of salt, kilograms of solvent. Molarity uses volume of solution. So if I have my beaker of salt water, the moles of salt are not going to change when I heat it. And the weight, the mass of my water is not going to change when I heat it. So molality does not change when you heat it. Why do you think we use molarity in lab instead of molality?
It's harder to measure the grains in the volume.
Right. If you're working with water, it's a whole heck of a lot easier to pour it in a graduated cylinder, take the reading, and use it, rather than having to weigh everything. Imagine having to weigh 1,250 grams of water. You're going to take a guess, and then you're going to take a dropper and go drip, 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 and then you're going to quit and go home. Okay? Whereas you get a graduated cylinder, you fill it till it hits the line, and then you're done. So let's calculate some molality. Here we have our KOH solution. That's the same. That was 56.7 grams. Now we've got lowercase m equals moles divided by kilograms. Which of those three variables are we trying to solve for? M. We're trying to solve for molality. Are we given moles? No. Not directly. Are we given kilograms? Not the right kilograms, because it is kilograms of solvent that we're looking for. We're given grams of solution. So we're not given either. We have to calculate both of them. Let's calculate moles. We have 56.7 grams of potassium hydroxide. Divide by the molar mass, and what do we get? 1.01. Thank you. Moles of KOH. That's our moles. How do we get kilograms of solvent?
You'd have to divide that by 1,000. Yeah. Where's the
Divided
salt?
by each row.
So we're going to have to divide by 1,000. But the key is that mass that we're given is the total mass.
See,
That's the mass of solution. We need kilograms of solvent. Right. And so I would do 245.8 minus the mass of the solute, the salt, or the KOH, to get the mass of the water. We need kilograms. How do we convert that to kilograms?
Divide by 1,000.
Divide by 1,000. So 0.1,
8, or not
1891 kilograms. Now we have moles and kilograms. We just go 1.01 divided by 0.189 equals 5.34 molal. It's also a lot easier to say molar than molal. Molal. Somebody's got to get a little pet mole and call it Al. So it'll be molal. Okay, that's where we're stopping today. So what's left on there are dilutions and colligative properties. Dilutions and colligative properties will not be on this exam. They are in that homework packet. And so try to find those questions and